right, today we are going to talk about the conservation of mechanical energy. Mechanical energy is simply like doing work. You have two main types of energies. What are the two main types of energies? It starts with a K and P. Potential, we use a K. For kinetic, we use a U for potential. There are two types of potentials though, right? Potential gravitational and potential from elastic. Good. Sometimes the U value, you have to put those two items together, okay? Especially if there's gravity and a spring. All right, so we're going to begin. Wow, something we need to remember about potential energy. I don't know. That'll be fun. Let's go ahead and see what that is. I went, phew. I don't know. Why don't we write this? I want to write U equals, what do I want to write? I don't know. Let's write U can be gravitational or elastic. Okay. Which could also be written as, it looks like I was thinking something else. I'm not too worried about it. We'll figure it out. What'd I write? Oh. Alright. We can begin by defining mechanical energy as the sum, like the addition, of its potential energy, that was lazy of me, and its kinetic energy. So remember, potential energy is U, kinetic energy is K of the system. Mathematically, we can write this as mechanical energy. Oh, I said I skipped a whole bunch of stuff here. I'm proud of myself. Oh, mechanical energy. Oh, I put that in there. Is kinetic plus potential at any particular point. For now, we are going to consider when there. For now, we will only consider systems that involve only conservative forces, so not friction, not tension, just conservative forces like gravity, spring constants. Okay. When a conservative force does work on an object in the system, that force transfers energy between kinetic of the object and potential of the system. Based on the previous relationships, we can find delta K was equal to, does anybody remember? Delta K was equal to, instead, and I'm not looking for 1/2 mv squared minus 1/2 mv squared, work, W, very good, the work done on the system. Does anybody remember what delta U is equal to? Negative work, excellent job. Therefore, delta K equals negative delta U. So, remember how like we had a ball when we would drop it? As like the potential energy would gain, the kinetic energy would lose. Okay, it was like a balancing act. Like up here, it's all what? Potential. When I dropped it, and right before I hit the ground, it was all what? Kinetic. But the addition between the two of them, let's say it was like 10 up here, it better have been 10 there, and 10 here, 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 here. But as one lost, the other one gained. So the whole time I had an addition of 10. This expands to the Kf minus Ki equals, negative, equals the negative value of Uf minus Ui. Does that make sense? Because they're change in kinetics and change in potentials? Is that okay? Okay. And we can rearrange that by distributing our negative in, right? So we can say Kf minus Ki equals negative Uf plus Ui. And here's the equation I really love, right? I just like the alphabet goes beginning to end. I love just saying, if I rearrange this enough, we can eventually say the kinetic energy at the beginning plus the potential energy at the beginning equals the kinetic energy at the end plus the potential energy at the end. I love this formula. This is for conservative forces only. Tomorrow, we'll talk about forces that are not conservative, forces that lose stuff because of friction or because of air resistance. Beautiful formula. So if at the very beginning you have a grand total of 10, at the very end you better have a grand total of 10. Conservative forces only. Do conservative forces exist in the real world? Nope. But this gives us a beginning point. Because once we understand this, and whenever you say like, hey, this and this don't equal each other, then we can start talking, well, how much is missing? And the amount that's missing is maybe your thermal energy or your frictional energy or your energy lost within the system. So it's the energy that just kind of, oh, in other words, oh, that's all I was going to put in there. That was my fancy equation I wanted to get to. If you guys look at the example problem I gave you from the Glencoe book, what do they don't use U's. Do you guys see how they use PE and KE instead of U and K? So I never actually used a U for potential energy, but that's okay. I think it's the more sophisticated method, so we'll go ahead and stick with it. All right, in an isolated system where only conservative forces cause energy trains, the kinetic energy and potential energy can change, but there's some of the system cannot. So what the heck does that mean? That means if you have, like, if you start with 10 joules, it's got to be 10 joules all throughout. Maybe the amount of each one's changing. Maybe you have 9 and 1. And then you have like 7 and 3, but they always have to add to 10. This is called the principle of conservation of mechanical energy. I tried to pick a fancy font. How did I do that? A fancy font there. Another way of writing this is delta E is going to be 0. The change in mechanical energy cannot change. Because, like, remember just keep that number 10. Like, the change in mechanical energy has got to be, you can't change it, otherwise you don't have a conservative force. So here they have to add a 10, here they have to add a 10, here they have to add a 10, here, you get the point. Everywhere they have to add a 10. Therefore, the change better be 0. And we can write that all kinds of, I should have just reprinted this so I didn't have to flip it all kinds of crazy. So we can say that change in kinetic energy plus the change in potential energy also equals 0. It allows us to solve problems that might be very difficult when we use Newton's laws. It really does make them very, 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 very easy. Let's just jump into it. I think you guys are gonna like them. I like these. Oh, I'm not even lying. Like, I was trying to find, I didn't creep too much because it was 10 o'clock at night, the time it was time, right? I was gonna put one of your faces on there. I was gonna creep online trying to find one of your faces. This is gonna be you all too soon. Ah, okay. At the end of graduation ceremony, it's coming.
If we have a graduation.
Oh, that's so true. I should have put your face on there though. Okay, let me add a preface there. If the coronavirus doesn't continue, at the end of your graduation ceremony, graduates fling their caps into the air. We can do it on Google Hangouts if you guys want, okay? Suppose that this is how big a cap is. A 0.12 kilogram cap is thrown straight upward with initial speed of 7.85 meters per second, and that frictional forces can be ignored. Now what we just said is the principle of conservation of mechanical energy applies. When we eliminate friction, we can say that Ke and plus, say I just said Ke and P. Then we can say that K and U add to the same amount the whole entire time. A, using kinematics. That was your first test, remember chapter 2? Use kinematics to find the speed. I put it in a fancy font. Find the speed of the cap when it's 1.8 meters above the release point. This is such a nice little review for you. We are actually reviewing. I could have asked you that question in chapter 2 and stopped there. You could not have answered B in chapter 2, but you could have answered A in chapter 2. So let's talk about some formulas. Or maybe we should talk about some givens. What do we got, guys?
Mass.
We got mass, we got initial velocity. So mass is 0.12. And initial velocity is 7.85. Good. Anything else acting on this system that we know of? Gravity is negative 9.8. This is in free fall, right, everybody? All right, so acceleration is negative 9.8 because we are in free fall. They might be like, it's not falling. Remember, guys, anything just let go in the air is technically free fall, whether you throw it up or whether you throw it down or whether you just let go. Yeah, y is under 1.18. Nice, I like it. Is that how far it gets? Okay, so that's like our position. So let's call where he lets go. Let's call that 0. Let's call y0 0, where he lets go, because that's his delta y. So if you want to, instead of writing these two things, you could have just wrote delta y as 1.18 if you like that better. That would be fine. All right, pick an equation. Do you have them memorized? No. I don't have time. Not y squared. V squared equals VO squared plus 2a delta y. Good. 2ax is how we did it horizontally, so it'd be 2ay vertically. So V, and I all put an F on there too. It's final velocity of what we're talking about. In fact, get rid of that. I don't want to screw you up. Okay, velocity of any given point, how about that? Squared equals the original velocity squared plus 2 times a times the change. In this case, delta y, not delta x, because it's not moving in the x direction. So v squared, we got this, is unknown. That's what they want us to find, if I'm not mistaken. VO squared is the same as VI. Are you guys okay in using those interchangeably? VI, VO, original, initial. Some people are really picky about it. Whatever, as long as you know what they mean. Plus 2 times, please use a negative 9.8 because we're talking about acceleration and that's gravity and that's going down. Delta y is 1.18. All right, add them up, take the square root, let me know what the velocity is. You could say positive and negative, but please don't.
6.204.
Okay. Oh wait, I'm sorry. What did you? I just wrote you. 6.2. Mr. McBurney only went 3 significance, so what's the 6.204? Okay. All right. Part B. Show that the mechanical energy at 1.18 above the release point. Show that I skipped this thing. Show that the mechanical energy at the release point is the same as mechanical energy at the top. Oh, at this point. Okay, guys. Here it is at the top. They're saying show that the mechanical energy here is equal to the mechanical energy here. So all we are really showing is that the mechanical energy at 0. And then we're going to prove that that's the same as the mechanical energy at 1.18. You ready? So the mechanical energy is kinetic energy plus, God bless you, plus potential energy. So that's 1/2 mv squared plus mg. Are you guys okay if I use an h instead of a y? Is that okay? I don't know. Use a y. It's the same thing, you know. What else? I have tissues. Okay. So let's go ahead and put this stuff in. So we have 1/2. What's the mass, everyone? 1.2. What is the velocity at 0 meters? What's the velocity at 0 meters? 7.85. It's at the beginning. Plus m, so 0.12 again, times gravity, 9.8, times the height. Nope, look what the height is.
0.
That's 0. So, in other words, when he releases it, we can say, we're going to say it's at 0, because they're saying please use this as the reference axis. What do we get? Good.
So that's 7.85 squared.
Yeah. I was going to say, Mr. McBurney definitely has 3.69. 3.697. Good. And we are in energy, so joules. Joules? J. All right, let's do the mechanical energy at 1.8. We're going to prove that we better get 3. We're getting this. We're doing that thing F loves where we get 2 of the same answers. Okay? So we do kinetic plus potential equals 1/2 mv squared at this point plus mgh at this point. I absolutely love this. So this is 1/2 0.12 times, what is my velocity when it's at 1.18? Good. Excellent. And that's squared, Amy Kathleen, plus m, so 0.12, g, 9.8. What's the height at 1.18? Good. Yeah, 1.18. Good. And we got?
3.697.
Yes. I don't know about you, but the fact that we use so many equations and plug so many things in and you end up getting the same thing to me is amazing. This is one of my favorite lesson of the entire year is right here. Well,
And
hey, you never know what we could be getting into with this so far favorite lesson